Hi everyone. So you should have watched the Chapter 5 Normal Distribution before you watch this lecture series, so you can take time now to go back and watch it if you have watched that. Right now we're going to focus on Chapter 5, Section 3, and the beginning of Chapter 8, so that will be Chapter 8, Section 1. So in this lecture series, we're going to focus on the central limit theorem. Until this point, we've worked with the distribution of a single sample of individual observations. This is every observation in the sample plotted individually on the curve. We got a sense of how spread out our data is, and we can also calculate the probability of getting an observation in a certain range. For example, for a population, the mean height is 69 inches with a standard deviation of 1. What is the probability that I randomly choose someone within 1 inch of the mean? So in the central limit theorem, what we're going to do is look at multiple samples. So let us now take multiple samples, or many simple random samples of some size n for a variable with any distribution. It doesn't actually have to be a normal distribution. And record the mean of each sample. We now have a distribution of means. The distribution of means will approximately be a normal distribution for large sample sizes. The average of the distribution of means approaches the population mean mu for large sample sizes. The standard deviation of the distribution of means approaches the population standard deviation divided by the square root of n for large sample sizes, where sigma is your standard deviation of the population. Let's take draws. So let's look at an example where we are taking multiple draws of strawberries. Each draw is conducted by taking a simple random sample of 30 strawberries. Let's say that we take 25 draws from the population of strawberries. In theory, we are endlessly repeating this process of drawing 30 strawberries at random. Let's just say that we only have data on the first 25 draws. If we wanted to look at the average weight of a strawberry, for each draw, we took the average weight of 30 strawberries. So in sample 1, I'm taking the average weight of the 30 strawberries. Sample 2, I'm taking the average weight of the 30 strawberries, so on and so forth. So the first point of the central limit theorem said that the distribution of means will approximately be a normal distribution for large sample sizes. What does this mean? It means that of the 25 draws that we took of size 30, so each sample had 30 strawberries in it, find the mean weight of a strawberry for every draw. The central limit theorem, if you continuously draw from a population, then the distribution of means will be approximately normal for large sample sizes. Per our example, if 30 strawberries are deemed a large sample size, and we continuously drew samples of 30 strawberries and recorded their average weight, then the distribution of the average weights of these samples will be approximately normal. So I can take this and I could create a data set. So each draw has 30 strawberries in it, right? Each of size 30. Each of these bowls will contain 30 strawberries. And then I'm going to take the mean weight of these 30 strawberries in pounds, and I'm going to do it for every single draw, and I'm going to record it in a table. Instead of using the word draw, we can say that each draw that you take can be considered its own sample. So instead of saying draw, I'm just going to say the sample that these means came from. So then using these means, I can create a histogram for our data. So let's say that the histogram of the mean weight for the strawberries looks like this. So as I said earlier, we don't sample the population only 25 times. The central limit theorem states that we randomly sample. So as I said earlier, we don't sample the population only 25 times. The central limit theorem states that we randomly sample the population endlessly. The central limit theorem also said that it does not matter what type of distribution we start with. If we are endlessly sampling this population, then no matter the type of distribution that we start with, whether it looks like this, whether it looks like this, whether it looks like this, if you were to endlessly repeat this process, as long as your sample size is large enough, then eventually all of them will convert to something that looks like a normal distribution. So in this particular case, this is, for instance, saying I'm endlessly drawing 5 strawberries for each sample, and I am endlessly sampling 5 strawberries. Eventually it will go down. If I were to increase my sample size and say 10, it will look like this. If I were to increase my sample size to say 30, it would look like this for each distribution, no matter which distribution you started with. 2 says that the mean of the distribution of means approaches the population mean mu for large sample sizes. So what does this mean? If the samples that we took are large enough, then averaging all of the mean from each sample should give us the same number as mu. So if I took all of these means and I took the average of all of these means, this would be my sample mean. So I'm going to call it x bar. If the number of strawberries in each sample is large enough to approximate the normal distribution, then I would expect my sample mean to be about equal to my population mean. 3 says the standard deviation of the distribution of means approaches sigma divided by the square root of n for large sample sizes, where sigma is the standard deviation of the population. What does this mean? If the standard What does this mean? If the standard deviation of the population is sigma, and our sample sizes for each sample are large, then the standard deviation for the distribution of means is sigma divided by the square root of n. So I keep saying we're looking at the distribution of means. Why? Because we are looking at all of these values, but each of these values are means. We're looking at the distribution of these means. So when my sample size is equal to 30, I can get the So when my sample size is 30, I can get the sample standard deviation, where the sample standard deviation is calculated using each of these as x, and then x bar is going to be the average of all of these averages, so it'll be my x bar, and you're just plugging it into the equation for the sample standard deviation. The central limit theorem says that if you were to endlessly repeat this process of sampling these strawberries and recording the average weight of these strawberries per sample, then the value of this s should be about equal to the value of the population standard deviation divided by the sample size that you drew from the population to begin with. So let's talk about the sampling distribution of x bar. Remember that x bar is our sample mean. For practical purposes, the distribution of means will be nearly normal if the size of the samples drawn is greater than 30. In general, the number is 30 for large, so you'll see is greater than or equal to 30. However, in your textbook, it actually puts a strict inequality and says that it has to be greater than 30. But 30 is typically considered okay and large. If the original population is normally distributed, then the sample means will be normally distributed for any sample size n. So that goes back to that image where we started out with a population that looked a little normal, a population that had even distribution, and a population that was skewed. But as you increase the sample size and you got a large sample size, all of them eventually became normally distributed. In the ideal case, where the distribution of means is formed from all possible samples, the mean of the distribution of means equals mu, and the standard deviation of the distribution of means equals sigma divided by the square root of n. So that allows me to create this notation here and then say that the sample mean is normally distributed with mean mu and standard deviation sigma divided by the square root of n. This is something that is extremely important to know. If the data for our sample of means is skewed, we would be unable to use norm CDF. Remember that norm CDF uses the z-score in the background, but to be able to use norm CDF, your distribution has to be normal. Now, the central limit theorem does say that you can start with whatever distribution initially as long as your sample size is large enough. However, this is the important note. The number of draws or samples was taken using a large sample size. The distribution of averages from each draw will be approximately normal. Or, the population is normally distributed, meaning that any number of draws will result in the distribution of averages from each draw to be approximately normal. So then we are able to use all of the rules for the normal distribution. Only when we have normally distributed data are we allowed to use a z-score transformation. And remember that the z-score transformation is done in the background of the norm CDF in your calculator. So, comparison of these distributions. When we're looking at the normal distribution, we have a single data value, x, which is normally distributed with your mean equal to mu and your standard deviation is equal to sigma. You have only one sample and your value of interest is x. But when we're looking at the central limit theorem, you expect your distribution of means, your x bar, to be normally distributed with mean mu and standard deviation is going to be sigma divided by the square root of n. Yes, this is your population standard deviation. However, when we're looking at x bar, the standard deviation of x bar is sigma divided by the square root of n, that entire quantity. So you have to have more than one sample where your sample size is greater than 30 or your original population of data is normally distributed. And in this case, your value of interest is x bar. If I were to compute z-scores for either of these distributions, this is what my z-scores would look like. You have your value of interest, you subtract the mean, and you divide it by the standard deviation for the distribution. So using that knowledge, we can now go through an example. It is found that the average weight of an adult snapping turtle in the United States is normally distributed with mean 31 kilograms with standard deviation 3.5 kilograms. We take samples of 7 turtles at random. What is the probability that the average weight is greater than 33 kilograms? So I've listed questions that I need to ask myself. How many samples are we looking at? One sample or more than one sample? If we're looking at one sample, we're just using the normal distribution. If we're looking at more than one sample, we're using the central limit theorem. But can we even use the central limit theorem? I then need to ask myself, what is my population? How is my population defined? What is my sample and how is my sample defined? Once I could answer those, I then need to see what are the values in reference to my population, aka what are the values of mu and sigma, or what are the values in reference to my sample, in other words, what are the value of x bar and n. Now that I'm looking at my sample and my sample size, is my sample size large enough to approximate a normal distribution? Or is my original population data normally distributed? In this particular example, we are taking more than one sample. because it says that we are taking samples of 7. So I'm looking at more than one sample, so I know that this falls under the central limit theorem. Then the next questions that I really do want to pay attention to are A and B. So is my sample size large enough? We're taking samples of size 7. 7 is not large enough. 7 is less than 30, so that doesn't qualify. However, B says, is my original population data normally distributed? If I were to reread this question, it says that the average weight of these turtles is normally distributed. So I'm actually able to use the central limit theorem simply because the average weight of what we are looking at is normally distributed. The population average weight is normally distributed. Therefore, no matter what size of samples I take, my sample means will be normally distributed. So now I'm going to go back to the 6 questions that we asked ourselves when we were looking at the normal distribution, and I'm just going to apply them to the central limit theorem. So step 1, identify your mean and standard deviation. 2, identify your value of interest. 3, draw a label and shade your density curve. 4, based on the density curve, identify your lower and upper cutoffs. 5, obtain the numerical answer to the question. And 6, explain your answer in words and context. Population mean is mu, and that is equal to 31. Here we know that our sample size is equal to 7. And we do know that this is not large enough to approximate a normal distribution, but we already noted that the average weight of turtles in the United States was found to be normally distributed. Therefore, we are actually able to use this. Since our original population of data is normally distributed, we can use samples of any size to estimate a normal distribution, so we can keep moving forward to continue through these questions. So my standard deviation for my sample means is going to be equal to sigma divided by the square root of n. So that's going to translate into 3.5 divided by the square root of 7. When we are looking at identifying the values of interest for the central limit theorem, we are looking at the sample mean in question. The sample mean in question is going to be x bar is equal to 33. Now I have to draw and label and shade my density curve. I would expect my density curve to look like this. Remember that in the middle of your density curve is always going to be your population mean or your sample mean, but we are talking about the central limit theorem, so my population mean is going to go in the middle. My value of interest is going to be 33, and then remember that we start shading the density curve in the direction of the value of interest. So we are looking for the probability that the average weight is going to be greater than 33, which means we are going to shade to the right of the value of 33, where in this particular case, my x-axis is x bar. So we are not using the empirical rule, especially when you're talking about the central limit theorem. We are definitely not using the empirical rule. So I do not expect to see any standard deviations written in here. I don't expect to see 31 minus 3.5 and that value minus 3.5, so on and so forth. We are using the idea that we are going to go forward with using norm CDF, so I only expect to see 2 values, your population mean and your value of interest, along with the associated label for your x-axis. Now remember that your x-axis always goes from negative infinity to positive infinity, and we denote this using negative E99 and positive E99. So in step 4, when we're talking about based on your density curve, identify your lower and upper values, we are interested in where your values of the shading starts and where it ends. So in this particular case, my shading starts at the value of 33 and it ends at positive infinity. So my lower is going to be 33 and my upper is going to be 1E99. Now I know that I need to plug this into norm CDF. So when I have my distribution of sample means, in my calculator, my mean is going to be my mu and my standard deviation value is going to be sigma divided by the square root of n. So this entire thing is my standard deviation, and that is what I am plugging in. Here I have labeled every single value of input in my calculator. So on your common assessment, what I expect to see is you label the lower value, label the upper value, label the mean, label the standard deviation. So essentially, if I were to get rid of all of the numbers in this first line, this is your chug and plug for your obtaining your numerical answer to your question. And then you're just filling in these values with the things that you found in the first 4 steps. So if I were to put this into my calculator, the probability that I get is 0.0653. Now, using this probability, I can explain my answer to this question in words. Here's an interpretation of a probability-based question for the central limit theorem. If we endlessly repeat the process of selecting n of whatever we're sampling and recording their average measure of whatever we're taking the average of, then the probability we would expect to see for the average measure of whatever we're taking the average of to be where is your density curve shaded, value, interest with measure, is what is the value of the shaded area in your density curve. So to plug that in, it would look something like this. If we endlessly repeat the process of selecting 7 turtles and recording their average weight, then the probability we would expect to see for the average weight to be greater than 33 kilograms is 0.0653. So I'm saying we have the sample size 7, we are sampling turtles, we are recording the average weight of the turtles, then the probability, because we're interested in probability based on this question, we would expect to see for the average weight, the x bar, to be greater than 33, the direction that you're shading with the value of interest is the value that your calculator spat out, this 0.0653. If I were to change the question instead to look at percent, this would be one of the options that you have for interpreting your percent. It's basically the same thing, except we are now looking at the percent of time here. So plugging that in, we can say if we endlessly repeat the process of selecting 7 turtles and recording their average weight, then about 6.53% of the time, we would expect the average weight to be more than 33 kilograms. So you're just taking the value of your probability and you're multiplying it by 100 and adding a percent sign at the end. So here's some comparison. When you're talking about the probability distribution of a random variable or a single value, you are looking at the phrasing of a question where it will say, what is the probability that A? Versus when you're talking about the sampling distribution of the mean, aka we're talking about the central limit theorem, what you're going to look at in the phrasing of the question is, what is the probability that the sample average, or what is the probability that the sample mean is? And these would be your z-scores to calculate whether or not you have some type of typical or unusual value in your data set. So for example, students in the 2011 graduating class who took the ACT scored an average of 22.4 on the mathematics portion of the test, with a standard deviation of sigma is equal to 5.1. A simple random sample of 40 students who took the test is selected. What is the probability that a random student will have a score higher than 22? Versus, what is the probability that the sample mean will be greater than 22? So again, you're looking for A, or you're looking for a sample mean. This goes back to that idea of how many samples did you take? Are you looking at a single sample, or are you looking at more than one sample? If you're looking at a single sample, we're using the regular normal distribution information. If you're looking at more than one, you're looking at the central limit theorem. I could also have it where it says, what is the probability that the mean will be greater than 22? So it doesn't even have to use the word sample. You just know that you're looking at a mean. A mean is a collection of numbers that are being averaged versus a single number. And I could also have it where it says the word average, because remember, the words mean and average are synonymous. And this is going to be the end of the lecture series for the central limit theorem. So now that you've actually listened to these and gone through these take your time now to actually go into the Canvas site, and underneath the Files tab, what you will find is an example worksheet that you can go through that will best prepare you for the common